did have a few questions on the discussion topic that I posted. So just running through those real quick. First one was about wave particle duality, and all electromagnetic radiation behaves in both ways, both like particle and both like wave, or in both ways like particle and wave. But different energy levels behave more like one or the other. And the low energy, like visible light and flow, behave more like a wave, so more like pure energy. Even though it does have a particle property to it as well, it does behave more like a wave, as opposed to the upper register where you get into X-rays and gamma rays and possibly some upper, very high upper visible light. It behaves more like a particle. So low energy, wave, visible light, wave, and then X-rays and gamma rays especially more like a particle. So, you know, I'm not going to throw something at you that says anything other than that. X-rays and gamma rays behave more like a particle. More like a particle being the key there, because they do also behave like a wave, just more so like a particle. Okay, as opposed to low energy, more like a wave than a particle. So infrared energy, you know, the other questions were about infrared energy and where we deal with infrared energy. And infrared energy is just heat, right? Mm-hmm. So inside of the tube housing, the protective housing, which we'll talk about in detail later in the semester, is where we deal with it and how we deal with it is in the three different ways that we talked about. We've got conduction, convection, and thermal radiation. And conduction occurs in a couple of different places. First off, we've got a big anode. The anode surface is really large, right? But we only use a very small portion of it at any given time. So looking at the face of the anode, we got that, but our actual focal spot's only about that big. So it gives the heat a lot of places to go. So it can conduct all around the surface so that it removes some of the heat from just that area right there. You remember looking at the anodes that I passed around, stationary anodes that I passed around first of the semester, and they were kind of melted, right? So if we put all of that heat in one spot, then what happens is it has a tendency to melt. It's going to melt anyway to a degree. It just prolongs it, so it gives it a place to go. So that's conduction. One place that we have conduction. Convection is movement of molecules, essentially movement of molecules. So what we've got inside the tube housing, just give it a key. There we go. What we've got inside of the tube housing is a fan, and the fan blows air. So what we have is a couple of things going on. Inside the tube housing, we've got all this oil, right? And so we've got the conduction from the actual focal spot across the face of the anode, and then what happens is it has a tendency, or it doesn't have a tendency to, it's going to thermally radiate to the glass. And so that is your thermal radiation. One place we have thermal radiation. So it goes to the glass, but the glass is in contact with the oil, so we again are back to conduction. In the second place, we get conduction from the glass into the oil. The oil heats up, but then if we blow the air across the surface of the oil, the fan's not in the oil, but the oil's given off some of its heat in the form, again, of thermal radiation for a second time, and then you get convection, and the convection is blowing the heat off of the top of the oil. Kind of like, you know, you take a cup of coffee or a cup of hot chocolate or soup or something, and it's too hot to eat or drink, and what do you do with it? Blow across it. You're convecting the heat off of it. Same principle, okay? So the three different ways that we deal with it is conduction in two different places. Conduction across the face of the anode, then conduction down, down into the oil. We thermally radiate from the anode down to the glass, and then again thermally radiate above the oil, and then we convect it by blowing it off. A lot of different things can control. What we'll learn later in the semester is that a lot of different things can control how much heat your anode can sustain. One is naturally rotate the anode to help with the conduction rather. We spread out the point of impact so that it spreads it out more evenly. So the faster we rotate that, the more heat capacity it will take, right? The better it conducts it. The more oil we have, the higher the heat capacity. You know, whether or not we've got a fan, and the top of fan can certainly affect it. Even the room temperature, the temperature in the room can affect it. Because if you're working in a trauma room, y'all been inside of a trauma room, right? It's like 90 degrees inside there. So with convection, what you get is drawing of air from the room to blow across the oil, right? So if it's cool in a room, do you suppose that would cool the oil down quicker than if it's 90 degrees in a room? It should, right? Cooler air is going to cool the tube down quicker than hot air, right? So a lot of different things can affect it, but the question was, where do we deal with it? And we deal with it inside of the protective housing in those three different ways. Okay. So the next question was attenuation, and attenuation is selective absorption. So X-rays attenuate, right? And attenuation occurs because X-rays, things are radiolucent, meaning that they pass through things, but you get some absorption. So on these X-rays over there, what you see is the results of that selective absorption or attenuation. You can see the difference, and I'm just going to point out the major differences because that would only zoom in so far, but you can see the differences between the lungs and the soft tissue and the spine because of attenuation. Different things absorb X-rays at a different rate. Bone more so than soft tissue more so than air, right? So it's selective absorption is all attenuation is. And how you see that, just in a practical sense, so now I'm going to spin that around and we're going to look at the window, or not really in a practical sense, but in more of a everyday life sense, is you see attenuation in the difference between the blinds and the window. Window's more transparent, the air can come, or the light can come through it, whereas the blinds are less transparent, so more of the light gets blocked. The plant, you can't see through the plant at all, right? Or if you imagine, you're driving down the road and it's really, really bright outside and you put your sunglasses on, is it so bad? No, because your sunglasses attenuate the light coming into your eyes. Same principle. And then you drop the visor and it gets even less so, right? Because nothing gets through the visor. None of the light gets through the visor. So, what's that?
If you're tall enough.
If you're tall enough, yeah. Or if you happen to have one of those cars that has the two-part visor that drops down a little bit further. So that's attenuation. Attenuation is partial absorption. It's not total absorption. So things that attenuate X-rays would be things that are radiolucent. Things that block X-rays are radiopaque. And then the other questions were about the inverse square law and the direct square law. So they're basically the same law, right? The only real difference is that the perspective that we're looking at. The inverse square law is always about dose, right? So your radiation exposure at 2 feet is X amount. What would your radiation exposure be at 4 feet? Well, you double your distance. As the inverse, which means things go in opposite directions. So you increased your distance. So your dose goes down, right? So you increase distance, dose goes down. You decrease distance, dose goes up, right? So you go, I don't know, you dose maybe 10 milliroentgens or whatever at, or the radiation exposure in air or whatever is at 2 feet, maybe it's 10 MR, right? You double your distance to, from 2 feet to 4 feet, what's your radiation exposure? Divide by 4, right? So it would be 2.5, right? So this is your radiation exposure is what the inverse square law shows. And the reason it does that is not because the X-ray beam gets any weaker because you back up. It doesn't. It spreads out. So, you know, at 2 feet, you've got that much. You know, your all of your X-rays concentrated in a small area like that. But when you back up, because of the divergence of the X-ray beam, it spreads out. So the same area here receives 1/4 the radiation exposure, right? So the direct square law is the mass compensation because that happens, right? So where you're going to apply the direct square law and how you're going to spot that in a test is if, you know, today you shot an X-ray on a patient at 40 inches, and at 40 inches you used, I don't know, technique of, let's say 80 kVp at 30 mass. You're shooting KUV at 40 inches. And you need to do an upright abdomen tomorrow. I should have done this with chest X-ray, but you have to, whatever reason, you have to back up 72 inches for the upright abdomen. So what would your technique change be? It would be the mass. And you went from 40 to 72 inches. So it's not quite double, right? It's not quite double the distance. What are you going to have to do with your mass, though?
It's going to go up.
You got to go up with it, right? It's the direct square law. So you increase distance, you increase your technique, okay? So in your direct square law questions, you're going to be looking for mass. In your inverse square law questions, you're going to be looking for exposure, okay? Now, to a degree, we refer to mass as exposure, but when we're talking about radiation exposure, that's going to be read out in things like gray and MR, things like that. It's not going to be mass. So if it says mass, you're looking for which law? Direct, right. So increased distance, increased mass. Decreased distance, decreased mass, right? So what we say the kind of the shortcut for changes from 40 to 72 inches will be, or 72 to 40 inches. 3.24, right? So 3.24, roughly 3 1/4, right? So you go from 40 inches to 72 inches, and you used 30 mass the first time. What's your new mass? Now we got to do math.
Divided by 3.24.
You went from 40 to 72. So you've got to multiply by 3.24, right? So that would be somewhere around 100 mass, right? Without doing, the actual math. Okay, so you understand what to look for in the questions. In the questions, I can't think of a scenario where your question would ask for an inverse square law question with mass included. So, if it's a mass question, and that's MAS, not MASS. If it's a mass question, then you're talking about the direct square law. If it's a radiation exposure question, your dose or the radiation dose at X number of feet is however much, and you increase, then your dose is going to be decreased, right? That's your inverse square law. Increase distance, decrease exposure for inverse square law. Increase distance, increase technique for direct square law. Always mass. Okay? So you good with those? Okay. All right, so what we're going to do today is we're going to start on chapter 4, and we'll go probably through, I don't know, get up to electrodynamics, but we're probably not gonna get past, I mean, we're not gonna start on electric circuits, because it really gets kind of complicated whenever we're talking about electric circuits. So we might go up through page 66, but we're not gonna go any further than that. We might not get that far, but that's the furthest we're gonna go. Okay, so now we're talking about actual X-ray creation and conversion of electric energy into electromagnetic energy. So remembering all the way back to the first chapter, we talked about all the different conversions that we're gonna undergo in order to create X-rays. So we get electric power from whatever power source we have, be it a nuclear power plant or whatever. I'm just gonna draw one line. So it comes to us in extremely high voltage, right? So let's just simplify it, around 500,000 volts. So very, very high voltage is what it comes to us. Then it gets outside of your hospital, and what does it have to undergo?
Conversion.
Hmm?
It goes through conversion.
Conversion.
Decrease.
So it's got to decrease from 500,000 volts, because that would just be a ridiculous voltage to have to deal with and manipulate. So we're going to reduce that down to, we're going to simplify it, we're just going to say about 100 volts. 100 to 200, really. And really it's 110 to 220, you know. But we're just going to say 100 to 200 volts. So it undergoes that on the telephone pole outside in the transformer, right? And then they feed that directly into the hospital, and it goes into your imaging system, and what's the first thing it gets to? It's been a while since we've done this, right? Okay, a type of transformer. The first transformer it gets to, though, has how many coils?
Wouldn't it be a lot? The high voltage?
Individual coil, like, I'm not talking about turns, but individual, like this whole apparatus. Is it one or two? It's just one, right. So we had a different name for this particular type of transformer. We call it a
Is it not primary?
auto.
Oh.
You got a primary side and you got a secondary side to every transformer, but it's auto transformer. And it does what for us? It allows us to do what?
To change the voltage.
To change the voltage. So we can increase or decrease the voltage. So we can turn it up, we can turn it down, we can increase or decrease the power. And in that way, it is a rheostat, or what we call a variable resistor. Okay? So how we work this thing is that we have set contacts on this side of the transformer. This side is called the primary or secondary side?
Primary.
Primary side. Primary side, regardless of which direction we're going with this, is the side that you supply the electricity to. Now we adjust the voltage by taking the contacts on the secondary side of the auto transformer, thank you, and either spread them out or pull them together. So if we spread them out, first off, if we have them in exactly the same spot, then the voltage on the primary side is going to be the same as the voltage on the secondary side, right? But if I spread them out, what's going to happen to my voltage? It's going to go up, right? So if I spread them out, voltage goes up. If I spread them out, if I bring them together, then the voltage does what? Goes down, right? So the voltage on the secondary side of any type of transformer is going to be proportional to the turns ratio on the primary side versus the secondary side. More on that later in the semester, okay? So then it comes out of that, and what does it go into? Bingo, another transformer. Now what's specific about this one?
It has
What?
2 coils.
It has 2 coils, it's number 1. Which coil is primary and which one's secondary?
The smaller.
Okay, the one on the left-hand side, because that's the one that we're gonna supply the electricity to. So we've got 2 coils, one on the primary side and one on the secondary side. And what we have to do is apply alternating current. Alternating current goes in one direction, followed by the opposite direction. So it goes in and out, back and forth, right? And it alternates, so it's alternating current. All of these work off of alternating current. So we've got alternating current creating a changing magnetic field in the primary coil. Now, if we move a secondary coil next to it and the number of turns are identical, secondary coil as on the primary coil, then what's our voltage change? It's a trick question.
It doesn't.
It doesn't, right. So we've done nothing. So what kind of voltage do we need?
Less.
Well, we've already got less. We went from that to this.
High.
We need high voltage, right? So we've taken our low voltage and we've adjusted it to the voltage we actually need. Now we need to boost it from voltage to, what do we use?
KVP.
Kilovoltage, kVp, right. So we move this secondary coil next to the primary coil, and the magnetic field, again, more on this later in the semester, but the magnetic field that's created here creates a changing charge in the secondary side. So alternating current creates changing magnetic field, which creates alternating current in a higher voltage. Now we went from voltage to kVp. This is actually our kVp selector. Even though we don't create kVp here, it is our kVp selector. That's where you're actually selecting your kVp. When you make those contacts on the secondary side, whenever you push the buttons to increase or decrease your kVp, that's what you're actually doing, is you're taking these things and you're spreading them out, you're mashing them together, okay? So it sets your kVp. It becomes kVp here. We come out of there, and what are we going into?
To another transformer.
We're done with this portion of the transformer. You're thinking about down here going into the MA selector, and then you've got the reverse of that where we've got a step down transformer. So we call this is our high voltage transformer, which is also a step up transformer, right? So we step up the voltage. This one, on the other hand, is a low voltage transformer. It's a filament transformer, and it is a step down transformer, right? So both of these feed electricity into the X-ray tube. This one supplies your amperage. This one supplies your voltage, so that when we get ready, we can send the electrons from the filament across the tube into the rotating anode, and the result is creation of
Heat.
primarily heat. Very good. Primarily heat. So what we get is creation of heat, mainly. Secondarily, what do we create?
X-ray photons.
That's thirdly. What's that? X-ray is third. What I say this thing was, the X-ray tube was basically just a big, complicated, expensive light bulb, right? So we create three different types of electromagnetic energy. We create mainly heat, a little bit of light, and even fewer X-rays, okay? So we get conversion and creation of those three things. So we get conversion of electricity into those three forms of electromagnetic energy, okay? So the primary function of the imaging system is to do just that, to take electricity that we're supplied and we're given, you know, a set amount of electricity or set voltage, power level of electricity. And there are some other things in here we're going to talk about later in the semester, but this is primarily where I want you to be right now. And we're going to manipulate that electricity to set a specific amount of electricity so that we can boost that up to a high voltage based on what we set over here, so that we can adjust the relative positive and negative charges inside of the X-ray tube, so that we can accelerate those electrons across the tube at a given rate of speed, so that we can create X-rays in the energy level that we need them to be, okay? A lot of words to say. We take electricity, we smack it into something heavy to create X-rays, right? The other two are byproducts of what we want to create, and unfortunately we have to deal with those when we talk about how we deal with the heat. The light's really inconsequential, it doesn't really matter to us. We can't see it, we can't use it, but it's there. And then the x-rays. So a very inefficient way of creating x-rays, that's the best we've got. The conversion rate of the electricity to x-rays is anywhere from, say, 0.1 to 10%, depending on a lot of different things. Okay, so very, very inefficient, and most likely, most of those are gonna occur right around 1 to 2%. Are gonna actually convert from electricity to x-rays. Very, very low percentage actually become x-rays. So how we get there is what chapter 4 is all about. How we get to that, or really not even how we get to that, but how we get to the point where we can take electricity and move it through a circuit to create all this stuff, to do all this stuff. Okay? In future chapters, we're going to talk specifically about individual components, but in this chapter, it's about the circuit, especially the first portion of the chapter. It's about electricity, how we use electricity, how we conduct electricity, and how electricity flows. Okay? So, we're going to start with static electricity. What is static electricity?
Friction?
Okay, that's a way to accumulate static electricity, and absolutely. Static electricity is, when we're talking about static electricity, that's the collection of electrons or an electric charge inside of your body. In wintertime, you're more prone to static electricity than what you are in the summertime, for reasons we'll talk about in a minute. But what static electricity is a collection of electrons. Okay, so in any atom, I'll take this off, just some of this off, because we're going to come back to this. In any atom, you got two charges. You got inside of the nucleus, what are your subatomic particles inside the nucleus that we're talking about? Protons and neutrons, right. Around the outside, we've got the electrons, right? So the neutral, or the neutron, has both positive and negative charges, and what we can say about the charges, both in the neutron and between the proton and the electron, is that even though the proton is massive and compared to the electron, the charges are the same, okay? So you got a positive charge and a negative charge. They're the same in magnitude. They're not the same, they're opposites, but they're the same in magnitude. So one proton, the amount of positive energy in a proton equals the amount of negative energy in the electron. So those two equal out, and in this way, an atom becomes neutral, okay? So the charges are opposite, but they're of equal magnitude. Does that make sense? So, what happens whenever you accumulate negative charges? You get static electricity. And most of the time it happens because of friction. You walk across a carpet and you drag your feet, right? Especially again in the wintertime, you drag your feet and then you get close to something metal, and what happens? You get shocked, right? And the reason that happens is because what you do is you accumulate negative charges. Now, we're not really going through the chapter in order here because we're kind of describing exactly how static charges build up. And it's by friction. All right, so you walk across the carpet, you pick up some electrons, you get close to something, and this is not a natural state for this atom, right? We've got one positive charge, we've got a neutral charge, so we're just gonna act like it doesn't exist because, you know, in this case, it's pretty indecisive. We're talking about positive and negative charges, and it's got both, right? So we got two negative charges, one positive charge, so this thing is negative. It's an ion, it's a negative ion, right? So it's got two negative charges, it doesn't like that, so it wants to get rid of one of those. So you get close to a doorknob, you know, anything metal, and what happens is it wants to discharge that extra electron and get rid of it. So you got this going on all the time. Most of the time, you don't notice it because the number of negative charges you build up discharges so quickly that you don't feel it. okay? The reason that you feel it more in the wintertime is because in the wintertime, we like humidity. Anybody else dry out in the wintertime? It's awful for me. I gotta keep, the only thing that works for me to keep my hands from actually drying out to the point where they'll split and bleed is mineral oil. So, mineral oil is basically baby oil without smell, and you find it in the laxative aisle, just in case you start having a problem. But I gotta keep it by my sink in my bathroom, and you know, every time I wash my hands, I gotta put some on before I dry my hands. Otherwise, I'll split and crack. In the wintertime, you'll see me with rubber band, or not rubber bands, but Band-Aids over the tips of my fingers,
I feel you there.
because they'll split and they'll crack and they're very painful. So the reason that you build up those static charges in the wintertime is because there's not the humidity that absorbs those charges. So you're doing this all the time. Anytime you're especially moving across a fabric, which you wear all the time, right? You're moving across any kind of fabric, you sit down in your car, you get up out of your car, you're rubbing across the fabric, you're creating a static charge. In the summertime, or any time except for winter, when the humidity's high, that humidity is absorbing those spare electrons. It's getting rid of them, okay? In the wintertime, the humidity drops, you dry out, and what you get is more and more of these charges build up. So, you know, you're never gonna have a situation where you get a hydrogen atom with, how many have I got there? 8 electrons, but if you have enough hydrogen atoms with enough spare electrons, then what you've got is a buildup of static charges you can actually feel whenever you get close to something. Okay? So, it's accumulation of static charges. Electrostatics is just that. It's the study or the acknowledgement, I guess, really, you don't necessarily have to study it, of a buildup of static electric charges. Electrostatics, stationary, they don't move. They don't move until you make them move, and we'll talk about that in a minute. They'll move eventually, but until you do something to discharge those electrons, they're stationary inside of your body. You're stuck, you're a great big ion. Now, the more electrons that you have built up, the more that charge is, okay? That's basically what we refer to as Coulomb's law, we'll talk about here in a minute. But the more of those electrons you have, the more you're gonna feel it whenever you reach and touch something that could discharge those electrons. Okay? So, electrostatics is just stationary electric charges. Charges can be positive or negative. We're only interested in the negative charges. So, what determines what an atom is?
Atom electrons.
It determines whether or not it's an ion.
Number of protons.
Number of protons, right. So your atomic number is just determined by your number of protons. So number of protons identifies what your atom is, right? So let's say you got a wire. What's the wire made out of? Metal. What's metal made out of?
Iron.
Okay, could be iron. Most of the time, if it's a wire, it's going to be copper, or maybe aluminum, probably copper, but what's copper made out of?
Atoms.
Atoms, protons, electrons, and neutrons, right? So you got, you know, protons, electrons, neutrons, so you got nucleus and you got electron cloud, and that's basically what your wire is. Okay? So in order to push protons being the essence of the material that we're talking about, in this case it's going to be copper. In order to push the protons, what I'm going to have to do? Let's say this is just a fundamental particle. Say copper in this case. Okay? So what would it be made of? Protons, neutrons, and electrons, right? So in order to take and move the protons on this piece of copper, what would I have to do?
Heat it up.
Yeah, you could heat it up, melt it to a point that it would flow, but in even in that case, what I'm gonna have to do is move the whole molecule, right? You can't move the proton. You can't move the proton unless you move the entire molecule. The proton is fixed in place and it can't move. But the electrons, on the other hand, we've already talked about how we can manipulate them and create something, a molecule that's a little bit different, right? We can kind of glue some together and create water. So we can manipulate the electrons. So when we're talking about the flow of electricity, what we're talking about is taking the electrons and moving the electrons down. We don't move the entire copper wire, we don't move the neutrons, we don't move the protons. We're talking about electricity and flow of electricity. We're talking about flow of electrons only, okay? So if we have a, let's say a situation where we've got two atoms, two identical atoms, and we're just gonna drop 8 on that one too. That might have been 8, close to it. All right, and then I were to push one more electron on this. What do you know about like charges? They repel, right. So if I push one more onto it, what are they gonna have a tendency to do?
Spread out more.
Spread out, right? Might they want to push one of these electrons off onto that one? You push the new one onto here,
Yeah.
you didn't like it, right? Somebody pushes something off on you, what do you have a tendency to want to do?
Push it on somebody else.
Push it off on somebody else, right? So if this one has a place to push it, what do you suppose is going to happen? Flow of electrons, exactly. So electrons will flow if you add more electrons to something. So back to here, if we've got electrons and we push more electrons onto a wire, then we get electric flow, okay? So we've got electrification, we've got electric movement, we've got electricity, flow of electricity. Okay, so in that way, when we talk about electricity, regardless of whether we're talking about electrostatics or what we'll talk about here in a bit is electrodynamics, what we're talking about is the negative charge, right? We have to have a positive charge because that's what the wire is made out of, but when we're talking about flow of electricity, we're talking about only the electron. Electricity, electron, right? So it's flow of electrons. Okay? So static electricity is just buildup of static charges. Okay, let me walk this back just a little bit. Whenever we're talking about electricity, we're talking about basically charged particles. So something can be electrified in one of two different ways. One, and the most common way, is to add negative charges because that's easy to do. Okay, but it's also relatively easy to do to remove electric charges as well. Okay, you scoop those electrons up when you're walking across the carpet. What are you supposed to happen in the carpet? Relative to you,
It's losing them.
It's losing them, right? So if it loses electrons, then what does it become?
Positive.
Positive, right? So electrification can actually happen in one of two ways. Either addition of electrons, in which case it becomes negative, or removal of electrons, in which case it becomes
Positive.
positive. Right, but you can't really do anything with positive charge. The only way the positive charge is helpful is, let's say this guy over here doesn't have any electrons at all, and we've added electrons here. What's going to happen to this guy?
He's gonna get some.
It's going to suck it up, right? So it might help to draw electrons, but for the most part, for our purposes, we can't use positive charge. So all discussion of electricity circles around the negative charge, right? But there can be positive charges and can be negative charges. So how does something become electrified? So 3 different ways, fundamentally. We talked about one being friction. You build up that static charge, you walk across the carpet, you scoop up those electrons, and you actually become electrified. So you got an electric charge. Electromagnetic devices are devices that use electricity, magnetism, one or both, to create electricity, or to manipulate electricity, electric motors, electric generators, those types of things. And there are such things as capacitors. So capacitors are kind of like a one-shot battery, all right? So what you've got is you've got electrons fed into this plate, okay? And there is like a dead space in between them, and let's say, because we've got all these buildup of electrons on this side, what does this become? Electric, or electrified, right? But what charge does it possess? Negative charge, right? So like charges repel, right? So they're trying to get away from each other, but they're stuck. This one over here might not have an absence of electrons, but in comparison to the negative charge that's over here, this would be relatively positive, right? So if I've got a distance in between those things, then the negative charges stay over here, this stays neutral, but if I move them close enough together, then what might happen? They'll jump. They'll jump, right? So they'll jump across and they'll equalize so that both of these become neutral. Okay? So no longer is one negative and one positive. It's basically what happens to you when you build up all these static electric charges is you become a capacitor. All right? So you're a one-shot battery. So you walk over to the doorknob, you get close to the doorknob, and what happens? They jump, right? Now Beauchamp, if you've read through the first part of this chapter, he says that we've got, things are electrified in one of two ways. Friction, which is rubbing. I started with friction and started back into rubbing. Friction, rubbing. All right. Then he talks about contact, and he says that contact is what happens whenever you touch the doorknob. And contact would happen if you touch the doorknob, but that's not really what happens when you discharge your electrons when you build them up. Okay? When you build them up, you've got the static electric charge through rubbing, but before you touch the doorknob, it jumps, right? And it's the same on a very small scale as what you see when lightning happens. We tend to think of lightning as coming from the cloud down to the earth, and really what you've got going on with lightning is equalization without any kind of touching at all. So the earth, in most cases, becomes very positive in comparison to the negative charge in the clouds, so it's it's kind of a cooperation between the clouds and the ground. So you get a relative positive charge on the ground, you get a relative negative charge in the cloud, and you get the jump of lightning in between. That's really what happens whenever you get close to the doorknob. If you walk in slowly and you watch, you get maybe a quarter inch away from the doorknob and you don't even touch it, it jumps. Where we actually have contact is like in switches. I got the dropsies today. Is the light on? No. So what you have in electric circuits, kind of the universal sign for a switch in an electric circuit is that. That's an open switch, okay? So are these two making contact? No, they're not. So electricity can flow down and up to that point, but it's not going to go anywhere else until you close the circuit, and now electrons can flow. That's what you're doing when you push the button on the light, okay? Is you're closing the contact so electrons can flow. That's contact, okay? Not the same as what happens whenever, the lightning strikes or you get the jump of electricity before you actually touch the doorknob. That's what we call induction. Contact is actual contact. Induction is something different. Induction is the jump before contact is made. So what you've got here are two different things. You've got a buildup in And then in these two cases, you've got equalization. Or the redistribution of electrons for everything to become neutral again is what contact and induction does. So flow of electricity for everything to become neutral again. So why does this happen whenever you get close to a doorknob or anything that's in contact with the ground? They say that the net charge of the universe and the net charge of the Earth itself is neutral. So when you scoop up those electrons, even with as small as we are in comparison to the rest of the globe, we become negative from the electrons that we've taken out of the Earth, right? So whenever we touch something, they're trying to go back home, essentially. So the Earth, the net charge of the Earth and net charge of the universe is neutral. So that the number of protons, number of electrons throughout the universe is equal, or even, right? So the net charge of the universe is neutral. Net charge of the Earth is neutral. So when you pick those up, they want to go back into the Earth. And the Earth is what we call an electric ground. So electric ground, what an electric ground is kind of like your warehouse or your storehouse for your electrons. You pick them up, they're going to go back to the warehouse eventually. Okay, so just a place to receive the electrons that you pick up when you're electrified. Now, we're getting into wintertime. Let's see if I can bring this up just real quick. We're getting into wintertime, and the practical application for this is enormous, essentially. So you pull up to the gas station, and what does the sign say? What does the sign say you shouldn't be doing if you're at the gas station?
Smoking.
Smoking, talking on the telephone, right? They've proven talking on the telephone really doesn't do anything. But what you should be worried about, first off, don't smoke. What you should be worried about is in the wintertime, build up static charges. Because whenever you reach for that doorknob and it's dark, what do you see? What do you see? You feel it, but what do you see?
Sometimes you see a spark.
Right, it's a spark that jumps.
It's like if you're in your bed and you have a fuzzy blanket and you lift it, sometimes you'll see
Exactly.
it. That's
Exactly.
weird.
Let's see. Let's run slow. But it's the same thing, yeah, especially if you have dissimilar fabric types, you know?
Is that like, I don't know, I saw this on a science thing one time. Like if you bite one of those
Surf?
Lifesaver candies, they'll
Yeah.
pop. It works. You
Yep.
put them in and they need to get in the dark, you bite them, and you'll see in the mirror.
Yep, you can see a little spark.
It's weird.
Okay, Mozilla Firefox not responding, let's go with Google Chrome and see. I'll get there with that. Okay, so wintertime, it gets cold. And you go to, let's see if I can find a different one, it's a little more dramatic even. You go pump your gas. So you get in your car, you go to the gas station. You're young, so you still got the quad strength to stand up without grabbing the car and pulling out. So you pull up, you go dig it in your purse or in your pocket for your credit card, you get out, and you swipe your credit card, right? You reach over, you grab the gas pump, the handle. So, by getting in your car and sliding across your seats, and then getting out of your car and sliding back across your seats, you reach for your door handle. What happens sometimes? You get shocked, right? So you get out, you've discharged at that point, hopefully. So you grab the gas pump. If you don't grab the gas, or if you don't discharge when you get out of your car, what's the gas pump made of? The handle.
She has some plastic.
It's metal. It's metal, right? So metal is a good conductor of electricity. That's why we use copper in the wiring. Metal is a very good conductor of electricity. Okay, so if you've still got a static charge and you reach for that handle, then you're going to discharge. You know, it's still hung up. So now you grab it and you stick it in your car, you squeeze it and lock it in so that it fills up, but it's cold outside. So what do you do? It's in your car, right? So you get in your car, what do?
Sliding across the seat.
Slide across the seats. You hear ka-thunk, that tells you what?
It's done.
It's done. So what do? Slide back out, right? So this is what happens. Sometimes is she gets out. She got a sweater or a hoodie or something, a lot of fabric there. So she's discharged all of her electrons. So we've got conduction, we've got induction, we've got contact. You know, her electrons should be gone. Now what's she doing there? Rubbing all over herself, right? Now, she gets back in the car. She almost got out, got back in the car again. Now she gets out. Click.
Okay, what are the chances of that actually happening now?
The chances are pretty slim that it could happen, but there's a way that you can prevent it from happening, okay? And that is,
Grounding.
you're never gonna have this happen with an 80-year-old. Why? You seen an 80-year-old get out of the car?
They just stand
Yeah,
there.
they touch the handle.
They grab everything. You know, they grab and they pull and they're touching everything metal before they get out of the car. Okay? I'm not saying that you gotta get out of the car like an 80-year-old person, but I'm saying before you grab the handle, you can prevent this from happening by touching something metal before you grab it. Touch the hood of the car, touch something, touch the gas pump again. Not the handle, but you know, reach over and touch the gas pump. The thing about gas is this, that the gas doesn't light. It's the fumes that light, right? So the gas pump itself didn't have just a whole lot on it. I mean, the gas will light if it gets to the fumes, but primarily the fumes are what causes a spark. So what's coming out of the tank as you're putting the gas in is fumes. So it's a very volatile situation. So if you have just the mildest spark, that can happen. Now she was smart, because what she did, and if this ever happens to you, keep in mind that it's the fumes that light, okay? So what she did was, she got that flare up, right? It flamed up, because there were a lot of fumes right there at the gas pump itself. She touched it, it flamed up, but what she did was she reached back in and she turned the pump off. You know, she disengaged the pump, took it out and laid it down. Where you really get into problems is when you panic, you know, because the only thing that's going to happen here is you're going to get that immediate flame up. You release the pump so it stops pumping. You give it just a second, and then you pull it out. And the only thing that possibly could be, you know, actually still burning is just in the neck here and right on the tip of the gas pump itself. So, providing you don't just grab the thing, you panic and you just grab the gas pump itself and you pull it out. Now what are you going to do if it's still running? You gotta hose your car down, right? you're gonna hose your car down and
One to town of Sales, Kentucky.
Oh, yeah, I'll be there in a minute.
Oh, and, I got out of the car, talked to my grandmother, and just grabbed the pump, put it right in the little, gas nozzle, and, started pumping, started pumping the gas.
Started
and
pumping.
got right back in the car, it was real cold. Sat there talking to her for not even a brief minute, you know what I'm saying? And listened to the radio, and then turned around, opened the door, you know, got right back out, leaned up against the car, grabbed the gas nozzle, and that was just like that.
so they pulled it out and hosed his car down.
They got there.
I'm done, I'm out of here. So the moral of the story is, discharge your electrons before you grab the pump handle. That's number one. You know, touch something to get rid of all that. That's number one. Number two, if you forget number one and you create just a flash fire, then all you gotta do is make it stop pumping first, and then you don't even have to pull it out, really. You just make it stop pumping and then walk over and just hit the red button that you should see at pretty much any gas station. It turns everything off, just as a precautionary thing. And at that point, you can pull it out, put it on the ground, and you can smother the fire in your car, in your gas tank, just by putting the lid on, the gas cap back on. And it's done. Don't hose your car down. And if you do, hit the red button and then run. So there's your public service announcement for today.
Now people are gonna think I'm crazy, cause I'm gonna be like.
You're gonna be touching everybody. Everything and everybody.
Yell at my husband, make sure you touch them.
What do you think about getting your car running while you pump gas?
Who does that?
Me, Evan, me.
Really? I'm so scared.
Yeah, you know, same thing can happen theoretically. You know, my first car it wasn't until 20 years later that my dad told me that it was a truck, it was a pickup. And he said that truck was the reason he stopped buying General Motors. He didn't tell me that for 20 years after he gave me this thing. But you pop the hood up and you got sparks just flying all over the place underneath the hood constantly. So same thing applies, you know, if you got a concentration of fumes and then you've got all the sparks going, you could create the same situation, you know, create a flash fire. So, yeah, you probably should turn your car off when you're pumping gas. Probably not a good idea to have it running. All right, so contact is equalization essentially by touching. Induction is equalization right before you've got touching. Friction is electrification. All three are electrification because something's getting electrified. You know, in our switch analogy over here, once we close the switch, we open the circuit by closing the switch, we got electrification over here where we only had it here. Induction, we got electrification of what is not electrified, and then in friction, you've got scooping up the electrons when you walk across the carpet or slide across your seat in your car. So when we're talking about electrification and buildup of charges, you know, the number of electrons we're talking about for a useful charge is a ridiculously large number. One electron, again, you can't do anything with it. So when we're talking about a useful charge, what we're talking about is a coulomb. And a coulomb is defined as 6.3 times 10 to the 18th power electrons. And we've looked at this number once before. So what we've got is 6.3 times 10 to the 18th power. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electrons for a useful charge of 1 coulomb. Okay? So a coulomb is just a measure of electrons. And there's a direct association between a coulomb and an amp. 1 amp is 1 coulomb per second flowing through a circuit. All right, so our units of radiation exposure, we have kVp and we've got amperage, right? So that's what we're talking about in amperage. So I said we were gonna get back to this, and we are. So when you set your MA, what you're setting is this circuit here. You've got some other circuits up here. You've got a timer circuit, so that when you make an actual exposure, you can measure the MA that you created and the time that you created the MA, so that you get your overall mass, right? So what is the M in MA? What does that represent? Milli, right, it's milli, and the unit of milli anything is 1/1000. Okay, so we say that creation of X-rays is very inefficient, and even if only 1% of our electrons become X-rays, so only 1%. 1% means 1 out of 100. So only 1 out of 100 of the electrons that we send across the tube become X-rays. Pretty inefficient, right? But until you really start determining the magnitude of the numbers that we're talking about. So if we have a 1 mass exposure, what that means is that we've got 1 in 1,000 amps, right? This is milliamp per second. So 1 in 1,000 amps, which 1 amp equals 1 coulomb per second. So 1 out of 1,000. Now, if I were to divide this number by 1,000, what's the easiest way to find the answer or solution to that?
Just take off 3.
Take off 3 zeros, right? Take off 3 zeros. Do I still have a lot of electrons? Yeah. So if only 1% of those become X-rays, how would I determine that? 1 in 100 of those become X-rays. Okay, divided by 100, so what would be the easiest way to come to that solution?
Take off 2.
Take off 2 more. So out of a 1 millisecond exposure, how many electrons or how many photons we're gonna have? Yeah, a lot, right? I'm not looking for an actual number, I'm just saying a lot of a lot of photons. We're still gonna create a lot of photons, even with a minimal exposure of 1 mass and a very poor conversion rate of 1 in 100, we're still gonna have a lot of X-ray photons created through the manipulation of electricity. Okay? So, electrostatic laws is probably as far as we're gonna get today. Electrostatic laws. There are 4 laws to electrostatics and how electrostatics behave. Okay? So just to run through them real quickly. What we've got is attraction and repulsion. Attraction and repulsion, different charges attract and like charges repel, right? So you got attraction and repulsion, we'll get back to that. We're gonna talk about Coulomb's law, which actually has 2 parts to it, so there's almost like 5 electrostatic laws. And then distribution and concentration, though, kind of go together. All right. Now, I'm gonna erase all of this. So attraction and repulsion. We've done this already, but just to do it again, if you have like charges, both electrons, then what's going to have, what are they going to have a tendency to do? Repel, right. So if you mash them together, if you try to mash them together, you try to push them together, then they're going to have a tendency to try to push against each other, right? So they push against each other. It's kind of like there's a magnetic field coming out of each one, because there really is magnetic field coming out of each one. So you push them together, they're going to have a tendency to push apart. So you've got like charges repel, right? But if I change one of these to a positive, then what happens?
They're attracted.
Exactly. They attract together, and essentially what you've got is a neutral charge. Right? So like charges repel, they push each other apart. unlike charges, attract. Okay? So, again, back to the analogy of you picking up electrons. You walk across the carpet, you got all these electrons gathered on your body. So they're all throughout your body. Let's make it on a lesser scale than that. Okay, you pick up a few. You've got some here, some there. What's the actual charge in between those? Are they going to be really uptight about being that close together if you got one on each arm, one on each leg, and one in your middle?
No.
Probably not. Okay, so more on that in a bit. Now Coulomb's law is where we're going to get into that. Coulomb's law has two parts to it. The electrostatic force. Electrostatic force is basically the force of the electrons. The electrostatic force is equal to the number of electrostatic charges. And part two, inversely proportional to the square of the distance between them. Right? So the first part of that, electrostatic force is equal to the number of electrostatic charges. Okay? So you've got a wire, and you've got two electrons on the wire. Your electrostatic force is basically 2. Okay? So if you add more electrostatic forces, more electrons, then your electrostatic force increases. Pretty much common sense. The more electrons you have, the more electricity you have. The more charge you have, the more charge you have, is basically the first portion of Coulomb's law. The more you got, the more you got. Coulomb's law, part 1. Part 2 is square of the distance in between them. Okay, so over here, this guy's got, let's say, an electrostatic charge of 5. But they're not really in too much of a twist. Why? They're spread out. Right. So these two electrons, our original two electrons, if we put them side by side, then because of the first law, they're going to have a tendency to push apart. Now the electrostatic force of them pushing apart is basically what we've got going on there. They're scrunched together, so they're going to push apart. So we've got an electrostatic force here, and it's pretty significant. But once it pushes itself apart, or they push themselves apart, what's the electrostatic force in between them? You still got two electrons, but are they doing anything really significant?
No.
The answer is no. Okay? So what does just that definition sound like? The second half of that. Inversely proportional to the square of the distance between them. They behave according to the, we talked about it the first part of the class.
The distance.
What's that?
One goes up, the other goes
Inverse
down. Opposite.
square law. It's the inverse square law. Behave according to the inverse square law. So the more distance you put between them, the less significant that electrostatic force. You still got the same number of electrons, but they're so spread out, they don't really care, right? So you bunch them all up, or you add more. There's Coulomb's law, first half Coulomb's law. You put a whole lot of electrostatic forces together, and what happens to your overall electrostatic force? It goes through the roof. Now you can walk across the room and shock somebody, right? But if you only have a few of them, and they're spread way out, according to the inverse square law, then our overall force is pretty minimal. What if I put them all right there? If you could. Could you still shock something? Yeah, probably so, right? Problem is, your conductor, that's never going to happen on you, but theoretically, yeah. If you could take all those electrostatic forces and put them together really tightly, then you can use them. Basis for a stun gun between that and the next two laws that we're going to talk about. All right, so the next one is really, kind of the inverse square law, and that is distribution. That is, essentially, electricity is going to find its own level. It's kind of like water. If I pour water on the floor, what's going to happen to the water? It's going to spread out, right? So it's not going to stack up. It's not gonna stay localized in one place, it's gonna spread out. Electricity is gonna do the same thing for different reasons, but it's gonna spread out. So distribution is gonna be even. You're never gonna have that on your person. They're gonna spread out across your body. So again, if you put two electrons on a conductor, they're gonna push themselves apart unless you have something to force them together. They're gonna push themselves apart until they find some sort of equilibrium where that like charge is not affecting each other, okay? Distribution is gonna be even on a conductor. A conductor is anything that conducts electricity, anything that allows electrons to flow easily, right? So a conductor is anything that allows it to go. So electrostatic charges are gonna spread out evenly on the surface of a conductor. But if I were to take this conductor, and I've got this thing that I made years and years ago in my office, and I forgot to bring it. But let's say we've got a conductor and we've got electrons, and because they're all negative charges and they all are kind of pushed each other apart as far as they can go, and I've got them situated like so, situated like that, that's enough. Are they evenly spread out roughly? Yeah, so I've got half of them on top, half of them on bottom, and they're kind of as far apart as they can possibly get. Now, if I were to take this wire and I were to bend it over, what would happen to these electrons on the bottom?
They would want to move away.
They would want to move away because you're mashing them together, right? But what would happen to the ones on top? The ones on bottom, if I were to bend them, the ones on bottom go like that, the ones on top go like that, right? So what would happen to these electrons?
They want to move on top.
They wouldn't want to move on top, right? So we've got the electrons are going to spread out evenly on the face of a conductor, but they're going to concentrate on the tip of the sharpest curvature. Okay, anybody ever seen a stun gun? Okay, the tip of a stun gun is either got a little ball on it like that, or it's got a point on it like that. And the reason for that is because you concentrate the electrons on the very tip of something, and you can zap somebody, okay? Anybody been to surgery? Okay. You were probably, at some point you're gonna get to surgery and you're gonna pay attention to more than just the surgery or the tech. What I want you to pay attention to is the anesthesiologist at some point. Anesthesiologist is always at the head of the bed. And what he does, he gives the gas and he gives the drugs to keep the patient asleep. And some of the procedures that they do in surgery, they give the patient a paralytic. The anesthesia is actually a paralytic. So if they're doing brain surgery or spinal surgery, they don't want the patient to move at all. So they artificially induce a paralysis so the patient can't move. But I've seen patients where the paralytic loses its effect and the patient starts to wake up on the table. So you've got a knife in somebody's spine, you don't want them trying to get off the table, right? So once in a while, the anesthesiologist will test the patient to see if they're still paralyzed. What he's got is he's got a miniature stun gun. And the thing is only about that big, and he's got these two electrodes that come out of it. And when we're talking about things like stun guns, what they use is very high voltage and very low amperage. Amperage is what will kill you. You put enough electrons through somebody, they're gonna die. High voltage, though, makes you feel like you're gonna die, but it's pretty harmless unless you got pacemakers or something like that. So what he's got is basically a little stun gun, and it might have, maybe a little bit bigger than that, but it's got maybe a couple of different buttons on it. So what he does with that, it's got a little bitty transformer inside of it, so it uses low amperage, very high voltage. What he does with that is he puts it right up against the patient's temple. It's pretty awesome. He puts it right up against the patient's temple, and he energizes it. And if the patient goes like that, they ain't paralyzed, so he gives them a little bit more. It's hilarious.
Oh, that's awful.
but,
Not even later? Like,
No.
they don't feel like,
No.
oh, I.
no, we used to have fights with those things.
Oh, okay.
I spent most of my career in the OR. Somebody be sitting there scrubbing the blade that, you know, they use to intubate somebody. You walk up behind them, you hit them right on the back of the neck. Their arm just flies, you know, just stimulate the nerves. But it's using all of this. What it's got is because these little balls, we're concentrating the electrons on a conductor that's bent very sharply so that we can use a very small charge, relatively speaking. It's only a 9-volt battery inside this thing. So it can't possibly truly hurt you. Make you feel like it's gonna hurt you, but can't possibly really hurt you. Just to, you know, stimulate, to see whether or not the patient's still knocked out. We came in almost right on time. Any questions on all that? So just running back through, electrostatic charges, like charges attract, or unlike charges attract, like charges repel. Coulomb's law has two different parts to it. Electrostatic force is equal to the number of electrostatic forces. The more electrons you have, the more electrostatic force you have. The more you have, the more you have. But if you spread them out, then that force becomes less significant. So it behaves according to the inverse square law. They collect evenly on a conductor, but they concentrate on the sharpest curvature with the 4 electrostatic laws. Okay? Any questions?
The exams are Friday, 6 to 7.
Yeah, something like that. Or, 60 questions on this one?
Isn't it usually 30 or 40 on?
Yeah, I'm thinking the one on Friday is only 30, 40,
Okay.
but the next one, next chapter, this one is supposed to be 60.
Well, we know our grades that day.
Yep, everybody will be on campus and, you know, we'll split you up and